Konnichiwa. So today we are going to be looking at integrating some functions that can be a little bit tricky because we don't actually get values which they integrate into. So if you recall from one of our previous lessons, we had a look at some of the functions that you need to learn off by heart. So that's these ones here. So I'll just move this out of the way for you for a second. So here we go. You can see that they were given integrals for cosine, sine, sec squared x, cosec x cot x, cosec squared x, and sec x tan x. However, we're not given the integral, for example, tan x just on its own, or some of the other values, for example, cot on its own, or cosec x on its own without the squared there. So to overcome this, we're going to need to be using some of our identities and just getting used to the fact that we're going to be using these identities over and over again, not just to solve trig equations, but also to help us with integration. So let's go on to our first example. So here it is. We are looking at integrating tan squared of x. And if you recall, again, from that list, there isn't anything there at all for tan squared of x. Tan squared of x isn't listed. Something that we have got which might be of use if we think about the different identities, you might think of sine x over cosine of x, but that squared really adds a bit of difficulty there. And if you consider something else that involves tan, and we're sort of looking at this list, we can see that sec of x and tan of x are linked. Let's have a look and see if we can remember one of those identities. So we know from earlier on in the course that some of the identities that we have include that 1 plus tan squared of x is equal to sec squared of x. And as we saw from that little example I had there, we can integrate sec squared of x. We've been given a value for that. So I'm going to take this identity and use it to make a substitution. So if I rearrange for tan squared of x and make that the subject of the formula, I'll have sec squared of x minus 1. So that's what I'm going to do. I'm going to take out the tan squared of x. I'm going to replace it with this sec squared of x minus 1. So finishing off the question, we know that when we integrate sec squared of x, we get back tan of x. When we integrate minus 1, we're going to get minus x. And then not forgetting, because I've got no limits on my integral, that we then need to have that plus c. And that's the first example done. So our second example, here's another pesky squared function there. It seems to be causing all of the problems. So sine squared of x, you can separate that for sine x times sine x, or 1 minus cosine squared x, but you're still going to end up with that same issue of this squared here and trying to integrate something like that. So what we need to do is consider where else we see sine squared x, what other identities can we use. So yeah, hopefully you remember that for sine squared of x, I've always said to consider the cosine, the double angle formula for cosine. So cosine of 2x, it has got several versions. You've got the 2 cosine squared of x plus 1. The version that we're going to be interested in, though, is the one that involves the sine squared of x, so 1 minus 2 sine squared of x here. So if cosine of 2 of x gives me that, then rearranging, I'll get that 2 sine squared of x is equal to 1 minus cosine of 2x. And then sine squared of x, isolated on its own, can give me 1 minus cosine of 2x, all divided through by 2. So what I'm really looking to integrate here then is I'm going to replace that sine squared of x for this function here. So I will get 1 minus cosine of 2x. I'm just to split that, so I've got a half, and then I've got that over 2 there with respect to x. And then my limits again here, so pi over 8 and pi over 12. So let's continue and see what we get. There we go. So integrating the half is obviously going to give me sort of x to the power of 1. That's still going to be over 2. Now, cosine of 2x, let's consider what happens here. So I know I've got sine, cosine, minus cosine. So if I'm going from minus cosine and I'm integrating and I'm going anti-clockwise, so I'm going to have something involving minus sine of 2x. And now let's consider what happened when I differentiated. So when I differentiated sine of 2x, that should have involved the chain rule. So I should have had 2 cosine of 2x. Let's have a look though. Do I have at the beginning of this section here, somewhere, do I have that 2 which I should have had? No. Worse than that, I actually have a divide by 2 here. So not only would I have been originally looking to divide it by 2, I'm now going to have to divide it by 4, because that's the only way that this expression, with dividing it by 4, that's the only way that expression could have ever come out to be what I had here, which was cosine of 2x over 2, like that. So I'll just go over that again, sort of in black. There we go. So that's what it is integrated. There's no plus c on this one because we have our limits. So I've got that pi over 8 and pi over 12. So to finish the question this time, what I need to do now is substitute those values into the expression. Okay, so I've skipped ahead a little bit there and just substituted those values in. So the blue is where I've substituted in x for pi over 8, and the green is where I've substituted in for x equals pi over 12. So on the left hand side I'm going to get pi over 16, take away. Now this 4, I'm going to just take that as a quarter, and then the expression that I get at the top here is going to be sine of pi over 4. That gives me root 2 over 2. And then I'm going to subtract from that. Okay, be careful because you need to subtract everything from this side. So pi over 12 divided by 2 is going to give me pi over 24. Then again, I've got sine, and this time that's going to give me sort of pi over 6. Pi over 6 gives me a half. And I've still got this 4 in my denominator, so that's a quarter there. So in total, what I've got here is going to be, so pi over 16, take away the pi over 24, that's going to leave me with pi over 48, and then I've got subtract a quarter of root 2 over 2, the minus here is going to give me plus a half. Okay, so overall that expression will tidy up to give us pi over 48, and then if I sort of work through that quarter there, so expand my brackets, etc., it tidies up to give me 1 minus root 2 all over 8. And that's how you would want to leave it. You wouldn't want to evaluate that pi because leaving pi there is in its most exact form. Similarly, for that root 2, that's the value in its most exact form. Okay, so just 2 more examples to go through. This next one is sine 3x cosine of 3x, and I'm hoping that sort of rings a bell, really, sine and cosine together. This is a bell that I hope it rings, is my double angle formula for sine. So you hopefully remember that gives me 2 sine x cosine of x. Okay, now that doesn't really look very similar to this, but we can manipulate it so that it does. So if I were to say go for a sine of 6x, because I notice the pattern here is whatever I've got in front of there, the coefficient of x on this side is half of that amount. So I'm going to go for 6x so that I can get that sine of 3x cosine of 3x. Okay, and then at the front there, we're still going to have that coefficient of 2. Still not quite what I want. I still only want to have that sine of 3x cosine of 3x. So I'm going to take this 2 and move it to the other side by dividing. So sine of 6x all over 2 gives me that sine of 3x cosine of 3x. So popping that into here, integrating sine of 6x over 2 with respect to x. Again, might want to consider drawing that out, sine minus cosine. So differentiating that way, integrating going that way. So that sine of 6x is going to become a minus cosine. Okay, I've got that 6 there at the start. So to compensate for the fact that I don't currently have a 6 at the front here, the way I would have expected to had I done the chain rule, I'm going to start by compensating with a 6th. But then you notice that I've also got this 2 here, so I also have got this sort of coefficient of a half going on at the beginning as well. And then obviously there, the cosine of 6x. So tidying that up, I will get minus a 12th of cosine 6x plus c. And that's your final answer. No substituting in limits here, as we had with the previous question. There are no limits, but that's why it's even more important to make sure that you're putting that plus c. Okay, so example 4, and probably going to be one of the longer ones to kind of work through. Having a look at sec x plus tan x, there is nothing immediately obvious. I can't see any pattern like the double angle formula. I can't see any identities that I can use because the tan x isn't squared, sec x isn't squared. So really, I think the first step with this one is just going to be slogging it out and applying that squared that we've got there. Remembering that with this, that means it's going to multiply the bracket by itself. We are not going to be just writing sec squared x plus tan squared x. Okay, so sec x times by sec x, sec squared of x, sec x times tan x sec x. Well, I'll put it in the same order as the previous one for simplicity. And then tan times by tan, so we've got tan squared of x. Okay, so let's look at what we've got now. Sec squared of x plus 2 sec x tan x plus tan squared of x. We know from our first example that we can't use that tan squared of x, but what we do know from our first example is that I can change that tan squared of x for the sec squared of x minus 1. So that's an identity that I can use now because I have it as a tan squared of x. So I'm going to substitute that now. So sec squared of x plus 2 sec x tan x plus sec squared of x minus 1. Okay, so putting that in place of the tan x there. Now I can tidy it up. So 2 sec squared of x plus 2 sec x tan x minus 1. Okay, so having a look through, can you integrate all of those values now? So from your formula booklet, you'll see that you can integrate sec squared x. So you can sort of give that a tick. I'm able to integrate that. You can also integrate sec x tan x. Okay, that's absolutely fine. We've got that there, and we know that we can integrate minus 1. Using your formula booklet then, sec squared x when integrated becomes tan of x. I have a coefficient of 2 there, so I'm going to make sure I put that coefficient back there. Sec x tan x when integrated becomes sec x alone. And again, making sure that I bring that coefficient of 2 down. And then the minus 1, integrating that becomes minus x, remember, doesn't disappear, we're not differentiating. And then again, finishing off your question, no limits, so we need to remember to put plus c to get full marks in an exam. If you wanted to keep it a bit tidier, you might want to just put brackets around your angles as well. And that's it, example finished.